What's up, guys? Welcome to Mathematics video lecture series. Today, I want to talk about a very important concept in complex numbers. Okay, and this concept is so important, and there is a reason why it is important. This is important because this concept is going to drastically simplify the problem solving complexity. Okay, and we'll see how. I'll give you ample illustrations to help you understand what do I really mean by reducing the complexity. The concept is known as de Moivre's theorem. So let's begin. de Moivre's, I often get confused here, but I think this is the right spelling. De Moivre's theorem. Okay, so let me take an example. Suppose there's a complex number z, r cos theta plus I sin theta. If I ask you what will be z to the power n, okay, and n is not a simple so as to say a simple small integer. It's not 2 or 3. Suppose I say n is very large, and let us say 1000 or any other large number, 568, some weird and strange number. If I ask you what will be z to the power n, then you will say, okay, no problem, I'll take the power of this complex number. So this will be r to the power n, obviously because it's a real number. R is a real number, so r to the power n, and cos theta plus I sin theta to the power n. Now this cos theta plus I sin theta is nothing but a plus, I can write it as a plus b to the power n. Now just think about it. If the power would have been 2, you will say, oh, it's a square plus b square plus 2ab. If it is 3, you will say, oh, again, a cube plus b cube plus 3ab bracket a plus b. What about 1000? So basically you need to use what we say permutation and combination, and you need to use binomial expansion, the concept of binomial expansion. But I said permutation and combination because in binomial expansion you will see NC terms, NCR. Okay, so how are you, it's going to be very lengthy. It will take you if I'll give you a pretty large number, it will take your lifetime to solve that expression. If I'll give you 10,000, okay, that's a weird joke. Anyways, so what to do? And there is a very elegant solution to it, and that is known as de Moivre's theorem, but it is essentially the use of the exponential form of complex number. So I've already explained to you the exponential form, so it's not very different from it. Let's try to solve it once again. Z is equal to r cos theta plus I sin theta. So instead of using this form, I will use r e to the power I theta. And why? Let's see why. Now z to the power n will be nothing but r e to the power I theta whole to the power n. So this will be r to the power n, correct? I to the e to the power I theta to the power n. So e to the power a to the power b is nothing but e to the power ab. So this will be e to the power I theta n. Just think, this can be written as this is a complex number whose magnitude is r to the power n, and e to the power I theta n is nothing but cos of theta n plus I times sin theta n. Wow, this complex number z to the power n is nothing but r to the power n cos theta n plus I sin theta n. Just imagine. Suppose I want to find z to the power 1000, it is nothing but r to the power 1000 cos 1000 theta plus I sin 1000 theta. Isn't this amazing? This is amazing, and this has reduced your time from a lifetime to 1 or 2 seconds. And you'll see this is so powerful, such a powerful expression, that you will often use this expression in solving complex number problems. Okay, let me take an illustration to help you better understand. If you remember, I told you about cube roots of unity. Okay, if you remember, the roots are 1, omega and omega square. Omega is nothing but minus half plus root 3 by 2 iota. This is your discretion whether you want to take this as omega or the other one as omega. Omega square is minus half minus root 3 by 2 iota. Okay, all of us remember this. We also know that 1 plus omega square is nothing but 0. Okay, now let us try to use, we solved this question using the simple cubic expansion method. Now we'll use de Moivre's theorem. Okay, so I'll say, okay, so z is equal to 1. I want to write it in polar form, so this will be magnitude is 1 and cos theta plus I sin theta. So it's 1, so theta will be, I'll have to take 0. So this thing will vanish and this is 1, so this will become 1. Very simple. Now I have been asked to find the cube root of 1. So basically 1 to the power 1 by 3. Essentially z to the power 1 by 3 is what I have to calculate. Okay, now what I'll do, I will write this polar form in a more general form. We all know that cos and sine have a periodicity of 2 pi. So instead of writing it as 0, I will write it in general periodic form. And what it is? I can replace any theta with 2m pi plus theta, where m is any integer. So suppose m is 4. So basically 8 pi plus theta. So you are rotating 4 times. You are making 4 circles and then coming back to theta, which is essentially the same thing. We all know this, that cos and sine have periodicity of 2 pi. Okay, so I can write 1 as 1 cos 2m pi plus theta plus I times sine 2m pi plus theta. This is general expression. This is equal to z. I want to find z to the power 1 by 3. So this will be nothing but 1 to the power 1 by 3. 1 to the power 1 by 3 is 1. And cos 2m pi plus theta upon 3 plus I sine 2m pi plus theta upon 3. And in this case, theta we have seen is equal to 0 degree. Okay, theta is equal to 0 degree. So this can be further written as cos 2m pi by 3 plus I sine 2m pi by 3. Now let us take different values of m. Okay, since we know that there will be 3 roots, so we'll take 3 values. So m is equal to 0. So it's essentially the same thing that we started with, cos 0 plus I sin 0. M is 1, m is 2. Okay, 3 integers. So what we'll get, the 3 roots will be cos 0 plus I sin 0. The other root will be cos 2 pi by 3 plus I sin 2 pi by 3. And the third root will be cos 4 pi by 3 plus I sin 4 pi by 3. For m is equal to 2. This is for m is equal to 2. This is for m is equal to 1. And this is for m is equal to 0. So this is nothing but 1. What will be this? Cos of 120 is nothing but minus half. Sine of 120 is nothing but root 3 by 2 iota. Cos of 4 pi by 3 is nothing but minus half once again. This is going to be in the third quadrant, cos of 240 degree. And sine of 4 pi by 3 is negative root 3 by 2 iota. And voila, once again we are getting the same thing. Let us assume this as omega, and this will be omega square. So using de Moivre's theorem, we have been able to solve for the cube roots of unity. It's a very interesting theorem. We'll solve more questions on it. Stay tuned. We'll meet in the next video lecture. Thanks for watching and have a nice day.